Hello viewers, I am Dr. G. Littleflower from Department of Physics, Stella College, Vijayawada. I am very happy to welcome you all to another interesting topic on basics of superconductivity. Let me give a little bit introduction about this topic. This magnificent universe manifests itself in two entities. They are matter and radiation. We all know matter exists in four states: solid state, liquid state, gaseous state, and the fourth state is called plasma state. Now, among these four, this solid state, materials in the solid state can be categorized into conductors, insulators, semiconductors, and superconductors based on the property called electrical resistance. So we must know what is called resistance. Resistance is the physical property of any material to oppose the flow of electric current through it. So if you consider conductors, they have less resistance and allow the current to pass through. Insulators, they do not allow, they have very high resistance and do not allow electricity to pass through them. Some examples: in our kitchen we use metals for cooking. They should be good conductors of heat. And copper wire, all this we use good conductors of electricity. Insulators are like ceramics, and the handle in the kitchen vessels can be insulators. And the third category, semiconductors, they have resistance in between these two, conductors and insulators. So the fourth category called superconductors, conductors and superconductors. Conductors have less resistance. Superconductors have no resistance at all. So what is resistance? It is the physical property of any material to oppose the flow of current. So if resistance is less, current can easily flow. If resistance of that material becomes zero, they can conduct electricity in an excellent way. So superconductors, this property of superconductors make them very, very unique and find superconductors to have remarkable applications. Also, this resistance-less nature help them to bring their transformative potential applications in the field of technology and scientific advancements. So now let us say, I hope you have got the brief introduction. Gives you some idea about what are called conductors. So superconductivity is a phenomenon in which the electrical resistance of certain metals and alloys completely vanishes when they are cooled to very low temperature. This phenomenon was first discovered by Dutch physicist Henk Kamerlingh Onnes in the year 1911. He was investigating the resistivity of mercury when cooled nearly to absolute zero. So he is a person. He received Nobel Prize in Physics during 1913 for this discovery in superconductivity. He observed that electrical resistivity of pure mercury drops abruptly to zero at about the boiling point of helium, that is 4.2 Kelvin. So here temperature we constantly mention in terms of Kelvin scale. So 0 Kelvin, 1, 2, 3, 4. So at 4.2 Kelvin, mercury completely loses its electrical resistance. So he concluded that at this lowest temperature, mercury has lost its resistance and it has gone into a new state which is called the superconducting state. The temperature at which the resistance disappears is called the transition temperature. That means the material from conducting state, it is getting transisted to superconducting nature. So this temperature is called transition temperature or critical temperature and is noted as T suffix C, Tc, critical temperature. The critical temperature of mercury, let us have from this graph we can understand. See, for example, this graph we take temperature in Kelvin along the x-axis and resistance whose unit is ohms is taken along the y-axis. Now we study how the resistance is changing with respect to temperature. So at room temperature the material may be having some high resistance. When you start decreasing the temperature, you can see the resistance of the material is going on decreasing. Actually, if it is normal conductor, it would have gone and met the y-axis here. If the material is a superconductor, so when you cool that superconductor, the resistance of it is coming decreasing, and at particular temperature, abruptly the resistance falling to 0. So completely the substance loses its electrical resistance. So here the resistance is 0. So the substance showing this property is called superconductor. So some examples we can take silver, lead, gallium, iridium, and so many are there. Here I provide a small table in which you can find out different elements like tungsten, cadmium, aluminium, mercury, niobium, technetium, so many, and their chemical formula is also given. Their Tc, critical temperature, is also provided. Okay, so we can, so for example, these are the elements, these are the alloys, combination of elements, that's why we call them as a compound. So for example, they have kept mercury, we said in the previous picture, 4.2 Kelvin, so approximately it is around 4.15 Kelvin it takes place. So here for this compound the critical temperature would be around 20.05 Kelvin, like that. So we can find out. Next, let us discuss some experimental facts which scientists have observed. So, what are superconductors? What are conductors? Normal conductors, when they are cooled to very low temperatures closer to absolute 0, they become superconductors. So, if you consider many elements, the existing elements at room temperature, and just compare their resistance, just looking at the resistance, we can guess which could become superconductors when we cool. So at normal room temperature, if we compare the resistance of elements, the elements which could become superconductors will have high resistance at room temperature. So at room temperature, superconducting materials have greater resistivity than other conducting elements. Then we said the transition temperature Tc. Transition temperature Tc is the temperature at which a conductor, or below which a conductor becomes a superconductor. So this transition temperature or critical temperature is different for different isotopes of the same element. So you must know what is called isotope. For example, hydrogen has 3 isotopes: proton, deuterium, tritium. Like that, same element but having 3 isotopes. That means their mass number varies and atomic number remains the same. In simple terms, we can say the proton number remains constant, whereas from isotope to isotope, the neutron number changes. So, same element, we expect same critical temperature, but the same element is having different isotopes. The isotopes will have different critical temperature or transition temperature. It decreases with the increasing atomic weight of the isotopes. I provide one example here. We just consider mercury. Mercury, for that the critical temperature Tc varies from 4.185 Kelvin to 4.16 Kelvin. So 4.185 Kelvin is higher, 4.16 Kelvin is lower. Now you see, when the critical temperature changes from 4.185 to 4.16, that atomic mass of that isotope changes from 199.5 to 203.4 atomic mass unit. That means as atomic weight increases, the transition temperature or critical temperature decreases. So this is very, very special point we should understand. Isotopes, their atomic mass, if it increases, the critical temperature of those isotopes decreases. This is one such example. Now it has been observed that critical temperature Tc of semiconductors found to vary as the square root of atomic mass m. So here I provide a figure. You can see here the atomic mass m, the logarithmic of the atomic mass m is taken along x-axis, and the logarithmic value of critical temperature is taken along the y-axis, right? So how they vary? As the logarithmic value of the atomic mass increases, you can see the logarithmic value of Tc is decreasing. That's what we stated here with the example. As atomic mass increases, the critical temperature is decreasing. So graphically we can show like this. And for semiconductors, they say that the Tc is related to atomic mass using this following formula. Tc is proportional to the atomic mass power minus half. So this minus sign says that when this atomic mass is increasing, this critical temperature is decreasing. So slope becomes negative. That's why minus sign. So formula wise, if we say Tc is directly proportional to m power half, you can see that m power half can be brought to the denominator m power plus, and then you take it to the left hand side, we get Tc into mc power half becomes a constant. So this graph depicts another interesting experimental fact that as atomic mass increases, the critical temperature decreases. Yes. Now, many elements will not appear in the purest form. Definitely there will be some impurities. Or you can just study what is the effect of adding impurities to the pure element. So, pure superconducting element they have taken and they added some impurities and they observed that the superconducting nature is not affected but the critical temperature is lowered. So, impurity does not have any effect, addition of impurities does not have any effect on the superconducting property. But what happens? The critical temperature is lowered. The presence of impurities in a pure conducting element lowers the critical temperature. And then using X-ray diffraction studies, they found that there is no change in the crystal structure. This shows that superconductivity may be more concerned with the conduction electrons than with the atoms itself. So, on the superconducting element, if we take and make X-ray diffraction studies, what they say, what they observed is there is no change in the crystal structure. This has direct idea that superconducting phenomenon is more of depending on the conduction of electrons than the atomic nature. Superconductors characterized by zero electrical resistance. So when there is no resistance, if you suppose you make a ring with the help of a superconducting material and using a battery, you just inject some current into the ring, that current in the superconducting ring will be persisting for years without any detectable decay. It is because there is no resistance. That superconducting ring does not oppose the flow of current. So the current given to the ring will be going on circulating in that ring without any detectable decay. let us see what are the effect of. We know the materials have different kind of properties. One is thermal properties, electrical properties, magnetic properties, optical properties. So many properties are there. Now we are taking a set of thermal properties. How the superconducting nature is related with the thermal properties. So first we take entropy. Another one we speak about the thermal conductivity. So entropy or thermal conductivity, they sharply change at the critical temperature or transition temperature. Normal conductor, when it is cooled and when it is below the critical temperature, they show remarkable change. Okay, thermal properties abruptly changing. For example, entropy, if you take. So what is this entropy? It is nothing but the disorderly nature of the arrangement of the atoms in the substance, right? So entropy in all superconductor increases as one passes from superconducting state to normal state. So in the superconducting state, atoms are arranged in the orderly state. So when a conductor is cooled from the normal state, it has disorderly state. Below critical temperature, it becomes a superconductor. That means it has attained the orderly state. Suppose superconducting property is irreversible. So from superconducting nature to normal conducting nature we could go. So if you increase the temperature, so in the superconducting state it is orderly, highly orderly state. So if you increase the temperature above Tc, it becomes a normal conductor. So that the orderly state gets disturbed and it becomes more of disorderly state. Then the thermal conductivity in superconducting state varies exponentially and is proportional to 1 by T. These are some properties. Then there is another set of properties called elastic properties. That means Young's modulus, bulk modulus, rigidity modulus, like that. All these properties do not change in transition. When normal conductors become superconductors, when below the critical temperature, the elastic properties of those materials do not change and they remain the same when the substance was in the conducting state and when it is in the superconducting state. Next, at any given temperature below the critical temperature, the superconducting property is destroyed on the application of the magnetic field called critical magnetic field. Now let us say that the substance is below Tc. That means it is completely in the superconducting state. Substance is cooled below the critical temperature Tc. So it is in the superconducting state. At this condition, now you have to apply a magnetic field and see what is the effect of magnetic field on the superconductor. What they have observed is when the substance is below Tc, it is a superconductor. At that state, when we apply the magnetic field and increase the magnetic field, at certain value of the magnetic field, it just loses the superconducting nature. So in the above discussion we said below critical temperature it is in the superconducting state, provided there is no magnetic field in the surroundings. Now it is in the superconducting state and now you apply the magnetic field and increase the strength of the magnetic field. We see that at certain magnetic field strength, the substance loses its superconducting nature. So that value of the magnetic field, okay, decreases as the temperature increases. So this point you will understand from a figure I have given here. You can see, you see the substance below Tc, it is completely in the superconducting state. Below Tc, from 0 to Tc, the substance is in the superconducting state. Now our interest is how or what will be the effect of applying magnetic field on a superconducting material. So what do you do? The magnetic field is represented by Hc, critical magnetic field. Its unit is millitesla. that is applied along the y-axis. Taken along the y-axis. So we are taking the temperature along the x-axis and the magnetic field along the y-axis. So now we know below Tc the substance is in the superconducting state. Now you increase the strength of the magnetic field from 0 to up. So when you increase the magnetic field like this, a particular magnetic field, okay, the superconducting material just getting converted into normal state. So it undergoes transition from superconducting state to the normal state. So the magnetic field at which this transition from superconducting to normal state takes place is called critical magnetic field. It's a very beautiful, remarkable fact which we should understand. So in the previous slide we said that as the temperature, the value of H decreases as the temperature increases. Last sentence, the value of H decreases as the temperature increases. So let us see, as temperature increases, what happens? The magnetic field is decreasing. The other way, let us say, as the temperature decreases, magnetic field strength is increasing. At one particular strength Hc, we find that there is a transition from the superconducting state to the normal state. So this magnetic field is called critical magnetic field. So now second parameter we have discovered through experiments. So initially Kamerlingh-Ohms defined superconductivity in terms of temperature. Now there is a second point he is bringing out. What is that? When it is in the superconducting state and if you apply a magnetic field, you see that when you increase the magnetic field at a particular magnetic field, the substance gets transisted from the superconducting state to the normal state, and that magnetic field is called critical magnetic field. The temperature below which, when it is in the superconducting state, is called critical temperature. This is critical magnetic field. So superconductors, that's just now I told, superconducting state of a metal mainly depends on the temperature and the strength of the magnetic field. Once again, the same picture I have brought for further discussion. Now, superconductivity is destroyed if a sufficient magnetic field is applied. So till here it is able to maintain the superconducting state. But if the magnetic field is increased beyond this, it just becomes a normal state. So superconducting state is getting destroyed when the magnetic field is increased. So this, or we can say the superconducting materials restores its normal resistance when a strong magnetic field is applied. So two ways, critical temperature and the magnetic field now controlling the superconducting state. Either you increase the temperature, it gets converted from superconducting state to normal state, or you keep the temperature constant. Below the critical temperature it is in the superconducting state. Now you increase the magnetic field. At certain magnetic field, it loses its superconducting nature. So two ways we can destroy the superconducting nature. So the magnetic field which is necessary to regain the normal resistivity is called critical magnetic field, Hc0. That means Hc0, now you can see the temperature is so much decreased. Now this is Hc0. The variation of critical magnetic field as a function of temperature is shown here, and we discussed also the value of the magnetic field when the superconductor loses its superconductivity is called critical magnetic field. If the applied magnetic field exceeds the critical value, the superconducting state is completely destroyed. Now from the figure we can relate the variation of magnetic field with the critical temperature using this formula. At any temperature T, Hc of T is equal to Hc of 0 into 1 minus T squared by Tc squared. What is called Tc? What is called T? Let us see now. So H of T is the maximum critical field strength at temperature T. At temperature T. That's why we say Hc of T. Hc of 0 is the maximum critical field strength occurring at absolute 0. Okay, and T is the critical temperature. T is the critical field strength occurring at absolute 0, and T is simply the temperature. Tc is the critical temperature. In general, higher value of Tc, higher is the value of Hc0. So here, I can take it to the here from this formula, this statement you can understand. Higher is the value of Tc. So you can see T is just temperature, Tc is critical temperature. So if Tc is higher, 1 by Tc value becomes very, very low. So 1 minus low value becomes some value, right? In that case, your Hc of T will be higher. If Tc is very higher, and then your Hc of T is decreasing. So that statement can be understood from this figure. You can see if Tc is very high, Hc of 0 will be very high. Suppose Tc is here, you have to, so Hc of T is decreasing. So suppose like that. So this formula beautifully relating the variation of the magnetic field with the critical temperature. Now, why this superconductivity is taking place? Why its resistance is suddenly becoming 0? This has to be discussed. Okay? The electrical resistance of ordinary metal is due to the collision of why current is not able to freely flow into the conducting material means because of resistance. What is current? It is the flow of electrons. So when the electrons move through this material, that material is made up of atoms. Under certain circumstances, some atoms the atoms lose their electrons, and they are ions. So we can say that element we can imagine in terms of lattice made up of these ions, and the free electrons will be moving. Those who have escaped from the atoms, they are called free electrons. The free electrons will be moving across the element. So these free electrons will be colliding with the ions there. So their speed gets reduced. So there is some resistance for the free flow of the electrons. So what happens? Their speed is reduced. So that the flow of current in such conductors will be restricted. Okay. Now this is normal conductors, I said. In superconducting state, something peculiar is taking place. These free electrons, what happens? They form pairs. How they form the pairs? Electrons, they have spin. They have magnetic moments also. So electrons can revolve clockwise or anti-clockwise. So now what happens among the free electrons? The electrons which have opposite spins and the magnetic momenta form pairs called Cooper pairs. This is another scientist, Cooper. He found explanation like this. Why at superconducting state there is no resistance? Same electrons only. Maybe I said in one of the experimental fact that X-ray diffraction says that there is no change in the structure when the substance is changing from the conducting state to superconducting state. So we said that this phenomena must be due to the conduction electrons. There is nothing about the atoms, locations and all. So that point is coming here. So among the free electrons, those electrons that have opposite spins and momenta, they just couple together, forming a pair called Cooper pairs. So they are coupled so strongly that they, without touching the ions in the lattice, they will be freely moving. So one diagram I give here, you can see these black dots represents the location of the ions in the element, in the crystal structure. Okay, crystal elements, we say crystal structure means that the atoms or the ions are beautifully orderly arranged. Now the liberated electrons, they form a pair. Which type of electrons can form this Cooper pair? Those who have opposite spins and momenta. So now what they do, they just move as a pair across the crystal. So the electron need not collide with this ion, it need not collide with this ion or any ion. The binding is, the pair formation is so strong, the bond between the electrons that have opposite spins and momenta will be very strong that they just freely move without colliding with the ions in the lattice. So they have no resistance. That is why at the superconducting state, the formation of Cooper pairs help the electrons to travel smoothly without having any collision with the ions in the crystal. So if they collide only, there is resistance coming, they lose the speed and the current flow gets restricted. Whereas in the superconducting state, electrons are not individual electrons, they are in Cooper pairs. So opposite spins make them to pair them up and they just smoothly travel across the crystal. So in the superconducting state, the electrons with opposite spins and momenta form pairs called Cooper pairs, and there is very strong attractive force between them, which is greater than the electrostatic force of repulsion. So these ions have positive charge, these electrons have negative charge. So definitely there will be repulsion. So when this ion repelling, this could come and collide here. So there is force of repulsion. But because of the spins, opposite spins, they experience an attractive force. This attractive force is much stronger than the repulsive force between the ion and the electrons. So there is no repulsion, there is no collision. So electrons could freely move across the crystal, and we say that this way, by forming Cooper pairs, this state, in superconducting state, the same element losing its resistance, there is no collision, so there is no resistance. So this explanation, I hope, will help you to understand. Thus all conduction electrons become a bound system. Now there is no transfer of energy takes place from these systems to the lattice ions. I hope you have understood. Okay, the electrons with opposite spins attract each other, which overcomes the electrostatic force of repulsion between the lattice ion and the electron. So because of this attractive force, the electrons remain in the bound system and they move freely without colliding with the lattice ions. That is the reason for the substance to behave like a superconductor, or you can say that in the superconducting state, the element has zero resistance. So if you apply some electric field across this crystal, you can make these electrons to move from one side to another side. Okay, thus they give rise to current. As these electrons do not transfer any energy to the lattice and hence they do not get slowed down, as a result of this, the substance does not possess any electrical resistivity. Okay, why superconductors do not have zero resistance means, here electrons in such elements in superconducting state, they do not exist alone, they are existing in pairs. In pairs, they gain additional attractive force, which help them to overcome the resistive force. So they easily current can flow through superconductors, right? It means that the resistance of the superconductor is zero. Next, one simple point I'll tell you. Yeah, Meissner effect. What is Meissner effect? In 1933, Meissner in 1933 observed that if a superconductor is cooled in a magnetic field below critical temperature, already we know when it is in a superconducting state, when you apply the magnetic field, what happens? So here, Meissner has observed that if a superconductor is cooled, this is just opposite of what we said. So when when element is in the superconducting state, when you apply the magnetic field, what happens? We saw that when the strength of the magnetic field is enough, then the superconducting state is getting destroyed. Here what we do, we take a magnetic field and we keep this conductor and reduce its temperature. So at certain temperature it becomes a superconductor. So it is still in the presence of the magnetic field. Now what happens? The moment it becomes a superconductor, the magnetic lines of force cannot pass through them. So with the help of a diagram we see here, we know magnetic field, we represent it by B. In the previous slide I represented H. B and H are related by B equal to mu naught H, where mu naught is the permeability of the medium, right? So you can say B or H, that means magnetic field is present. So electric field is represented in terms of electric lines of force. So same way the magnetic field is represented in terms of magnetic lines of force. They move from north to the south pole, okay, like that. So here we have represented the substance in the normal conducting state. Why you say normal conducting state? The temperature is above critical temperature. We know that when the temperature of the specimen is above critical temperature, it behaves like a normal conductor. So when it is a normal conductor, it allows the magnetic lines of force to pass through it. So in this magnetic field, we have kept the specimen in the conducting state. Now what we do? We are going to reduce the temperature of the specimen. So the temperature of the specimen, when it is becoming less than the critical temperature, you can see these lines which pass through. Now they cannot pass through the specimen. They cannot pass through the specimen. You can see the lines of force just changes its path and pass around the specimen. So you say in the magnetic field, when the specimen temperature is becoming less than the critical temperature, the specimen so far which behaved like a normal conductor becoming a superconductor. In superconducting state, the lines of force will be expelled out of the specimen. This effect is called Meissner effect. Okay. So here some statements I am giving. A superconductor, when it is in the normal state, the magnetic lines of force pass through it. You can see in the first part of the picture, the magnetic lines of force pass through the specimen. But when the specimen is cooled below the critical temperature, the magnetic lines of force are expelled out of the specimen. No magnetic line can pass through it. This is what called Meissner effect. So simple terms we can say, when a superconducting substance is placed in a magnetic field and when it is cooled, okay, when a specimen in a magnetic field is cooled and when the temperature is below the critical temperature, it becomes a superconducting element. This state, superconducting state, immediately we can feel that the magnetic lines of force are not allowed to pass through it. So the expulsion of magnetic lines of force when the specimen temperature is cooled below its critical temperature, when it is placed in a magnetic field, then this expulsion takes place. This is what called Meissner effect. Simple term we can repeat once again. Expulsion of magnetic lines of force by the specimen when it is cooled below the critical temperature in an external magnetic field is called Meissner effect. So, based on magnetic behavior, superconductors are classified as type 1 superconductor and type 2 superconductors. Type 1 superconductors are called soft superconductors and type 2 superconductors are called hard superconductors. So there are two types, soft superconductors and hard superconductors. Okay, so we are comparing the type 1 superconductors and type 2 superconductors. type 1 and type 2, they show Meissner effect below the critical magnetic field. Okay, even type 2 superconductors also shows Meissner effect below Hc1 and allow flux to penetrate this superconductor between Hc1 and Hc2. The material shows a mixed state called vortex state in between Hc1 and Hc2. So with the help of the diagram, we can understand the first statement in a better way. So type 1 superconductors, we have taken the external magnetic field along the x-axis and the magnetization along the y-axis. Now, when you increase the strength of the magnetic field like this, you can see magnetization. That means all the atoms will be orienting in the direction of the external magnetic field. So the magnetization will be increasing. At a particular critical temperature, suddenly magnetization becomes 0. That indicates that the substance has changed its state. It has become a normal state where all the atoms lose its magnetization. So the atoms turn into disorderly state. This is what called type 1 superconductor. In type 2 superconductor, the same thing. Here you observe a little thing. What happens? As the magnetic field is increased, like a type 1 superconductor, here also magnetization is increasing. At a particular magnetic field Hc1, what happens? It is not becoming, magnetization is not becoming 0. It is slowly becoming 0 at some higher magnetic field strength called Hc2. So here you can see magnetization is lost abruptly, but here magnetization is lost in the parabolic pathway, right? Slowly, gradually decreasing. So here for soft superconductors there is one magnetic field enough, but here this hard superconductors, they have two different magnetic fields between which the substance is in the mixed state. That means it allows the lines of force to pass through slowly, and then when the magnetic field strength become Hc2, completely superconducting state is destroyed and all the lines of force will pass through. So you have two magnetic field strength between which the substance is in a mixed state. So this state we represent it as a vortex state. That means between Hc1 and Hc2, the substance will be to some extent superconducting, to some extent normal conducting. So superconducting means it should not allow, here it is not allowing the magnetic lines of force. So here magnetic lines of force will be penetrating. So once again the same statement we can represent like this. Below Hc, the material is diamagnetic. That means superconducting is diamagnetic, but electrically it is a superconductor. So below Hc, the superconducting state is diamagnetic in nature, but electrically it is a superconductor. Now here below Hc1, the material is superconducting state and it is diamagnetic, but between Hc1 and Hc2, the material is in a mixed state and it is a electrically it is a superconductor. So along BC, between Hc1, BC and Hc2, the material is in the mixed state, superconducting as well as normal conducting nature. And some more differences are there. Above critical Hc, the superconductor becomes a normal conductor. Here the same point, between Hc1 and Hc2, it is in the vortex state, and if we still increase the magnetic field, okay, it becomes a normal conductor. Now type 1 are called soft superconductors, type 2 are called hard superconductors. Now for type 1 superconductors, depending on the nature of the material, if the magnetic field is around 100 Gauss or 100 to 1000 Gauss, you can see, you can convert them from superconducting state to the normal conducting state. But here in type 2 superconductors, the H2 value will be very large, many more times, even 100 times higher than the Hc of a type 1 superconductor. So they can produce very high magnetic field. They can carry large current in the magnetic field is between Hc1 and Hc2. So the hard superconductors find a lot of applications. So some examples I have given for soft superconductors: aluminium, lead, zinc, indium, gallium. For hot superconductors, the combination, the alloy, lead indium alloy and many more we can quote. So type 1 superconductors, in the superconducting state, the lines of force cannot pass through, they will be expelled. This is superconducting state. Okay, but in the vortex state, you can take this superconducting material like this. This is lines marked, they are called normal state. So the same specimen, different parts will be. This is in the normal state, normal state, normal state. Okay, normal part. Sorry. See, the lines crossed are marked as superconducting parts. So you can see the magnetic lines of force will not pass through. Same specimen only, but different segregation. Wherever the lines are marked like this, that parts will behave like superconductors, and you can see no lines passing through. But the part which is plain, you can see the lines pass through. So you say that the specimen is in a vortex state. So superconducting state as well as normal conducting state. Still, if you increase the magnetic field, slowly this conducting parts will be widened and the superconducting part will be narrowed. At one point of time, the whole specimen becomes in the conducting state. Okay, so that vortex state finds lot of applications. Now some applications I mentioned. Superconductors are used in medical field. So nowadays, instead of X-rays and CT scans, doctors suggest us to go for MRI scan. Okay, MRI scan, superconductors are used. And there is another kind of imaging also there, NMR. So NMR, nuclear magnetic resonance, also superconducting properties used, which will be used for imaging the body and know about the internal structure of the body. Okay, NMR is very powerful technique. Here also we use a superconducting nature, and in research labs, superconducting magnets in particle accelerators and reactors for nuclear fusion and all, superconducting materials are used. Superconductivity is main focus there, and this is the beautiful thing. When we walk on the roads, we can see the electrical cables crossing above the head, carrying the electricity, right, from the generating station to distribution center. Through the electrical cables, current is carried. Now if we at the generating station, how much they generate and pass it through the lines. At the distribution center, when we measure, some amount of the electrical power will be lost in the form of heat. This because those cables are made of conducting wires. Suppose if we are able to replace those wires with the help of superconductors, we know there is no resistance. So how much power you deliver at the generation station, exactly same thing will be reaching the distribution center also. That is a beautiful thing. So there is no power loss, higher efficiency, and the using superconducting materials. If electrical power is transferred, that entire process becomes environmentally friendly. I hope you would have understood what is superconductivity and the many experiment facts and the types of superconductors and some of the applications I have narrated here. If you want, you can go through the internet and find many more and read many more applications. So with this, I conclude this talk. We will meet in another interesting talk. Yeah, some more applications are there. Some more applications are there. Nowadays in Japan and China and all, maglev vehicles are there. So you can see here, this is a superconducting material, right? You can see this is normal magnetic field. If you place a superconducting material expels the magnetic lines of force, right? So magnetic field means it will be sending out the magnetic lines of force. the superconductor will not allow the magnetic lines of force to pass through. So as a result, what happened? These magnetic lines of force, the superconductor will oppose, so it is able to stand up in the air. So the same principle, this is due to the Meissner effect, expelling the magnetic lines of force. So the same principle is used in maglev vehicles. You can see that the track will be made up of aluminium, and when you pass current, magnetic field is produced, and there will be magnetic lines of force coming out of the tracks. The train base will be made out of superconducting material. So superconductors, due to Meissner effect, will not allow the magnetic lines of force. So as a result, the train as a whole just raises a few centimeters above the track, so that without any friction they can go very, very fast. Okay, in Japan and all, maglev trains are there which could travel more than 600 kilometers per hour. Suppose in India, if we take from Vijayawada to Delhi, actually within less than 20 hours we could reach from here. Otherwise, normal trains, if you take, at least it takes 2.5 days. Whereas if we have maglev vehicles, maglev trains, just within a day we could go. Okay, and the transport will be very cheaper also. And yeah, superconducting materials like tantalum acts as a gate and niobium as a control, and the system acts as a fast acting switch. And one more use is a squid, superconducting quantum interference devices. Superconducting quantum interference devices, they are used to detect the presence of any minute changes in the magnetic field of the human brain or body. Yeah, with this I conclude. I hope you have enjoyed today's talk. Many more applications are there. If you are curious, you can go through the internet or reading books and understand superconductivity. So it is one of the greatest blessing which is doing marvelously its a contribution to the society. Thank you, one and all.